Okay, so now that we have like the basic derivative rules and we have ones for working with trigonometric functions and we've got ones for working with how to apply a chain rule in there so we get an idea of composition, we're just going to add some more stuff into the mix here. And we're going to add in three things. We're going to add in inverse trig functions. We're going to add in how to deal with exponential functions, and we're going to add in logarithmic functions, okay, particularly e to the x and the ln of x. This could also, though, include a to the x, some any constant, and the log base a of x, but we'll kind of get into that in a minute. All right, so first we got to deal with these inverse trig functions. Okay, I'm going to give you a list of all of the inverse trig functions, but the two that you most need to know here are the ones for the inverse sine and the one for the inverse tangent, because they are the ones that come up most frequently on the AP exam. The other ones are like, if you're like got an extra night and you want to memorize some stuff, go ahead and do this. But the ones that I would definitely have committed to memory are the inverse sine and the inverse tangent. So the inverse sine one, it's not like very intuitive here. The derivative with respect to x of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. So this is completely not intuitive, and it is a very restricted domain. This is only going to be true on the domain from -1 to 1, because that's like where my inverse sine is kind of existing here. Because remember, the sine can only go between -1 and 1, so the inverse sine is stuck in that same restriction. Now, I'm actually going to prove this one, okay? Because this is like completely not intuitive. All right, so if I let y equal the inverse sine of x, this means that x is equal to the sine of y. That's what it means to be an inverse. And if I do a little bit of implicit differentiation, this is why this had to come after the implicit differentiation chapter. All right, this gives me dx is equal to, let's see, this is going to be the cosine of y. And then the chain rule, okay, says that I have to have dy dx here. Okay, so interesting note. This is 1 is the cosine of y dy dx, right? All right, so that works. But there's some weirdness here, right? Let's see what happens here. If I move this around a bit, I get dy dx is equal to 1 over the cosine of y. Well, that's all fantastic. But wait for it. I want this in terms of x. So I get some manipulation going on here. So note from above that x is equal to the sine of y, right? So note also that the cosine squared of x plus the sine squared of x has to equal 1. Okay, so what's that got to do with this, right? Well, let's see. That means that, let's not make those x's. I apologize. Let's back that up a bit. I got a little quick there. There we go. Still going to work. Let's make it cosine squared of y plus sine squared of y is 1. There we go. That makes more sense, because here, okay, this is cosine squared of y. We're going to leave that be for a second. Sine squared of y, well, x is the sine squared of y. There's the x squared, right? Because x is the sine squared of y. And then a little bit of manipulation here. The cosine squared of y is 1 minus x squared. Take the square root of both sides. The cosine of y is the square root of 1 minus x squared. And this is a cosine of y, and that's a cosine of y. So I can take that out and put this in. And I now have dy dx is equal to 1 over the square root of 1 minus x squared. Now, note, the sign goes between -1 and 1. This thing can't equal -1 or 1, so that's why my domain here doesn't have equal signs, right? Because remember, the inverse sign has asymptotes there at -1 and 1. Okay, so ultimately this is where my guy comes out, and we're in good shape. So this proves that this is true. Okay, so there's one. We did a lot of work. Commit that one to memory, right? Okay, so I'm not going to go through and prove all of these. Similar arguments can be made for the rest of them. So let's just list them all out. 1, the derivative, as we just said, of the inverse sine of x is 1 over the square root of 1 minus x squared. Number 2, if I take the, and that's on the interval -1 to 1. If I take the derivative of the inverse cosine inverse of x, it's just that with a negative sign. Boom. 1 minus x squared, and that's also on -1 to 1. So like literally, if you have the sign memorized, inverse sine memorized, just remember that the cosine is the opposite of that. The other one that you really need to know is the inverse tangent. Like this thing has come up like several times in this course, and you should know its derivative. It's 1 over 1 plus x squared. That's it. That's it. That's it. No square root, nothing. No minus, it's just that. All right, and then there's the deep cuts, like things that if you're bored on Friday night, you need something to memorize, you could memorize the cosecant inverse, right? The cosecant inverse is -1 over x times square root of x squared minus 1. Number 5, the secant inverse, right, is 1 over x over times the square root of x squared minus 1. Note, just like the sine and the cosine, these things just differ by a sign. Okay, so that's not so bad. And finally, the inverse cotangent, is, well, different from the tangent by a negative. So it's just going to be -1 over 1 plus x squared. All right, so that is the list of derivatives for the inverse trig functions. All right. Okay, so as promised, we're going to get you into exponentials and logarithms. All right, so when we talk about the exponential function, we're talking about the function of e to the x. So I want to say that the derivative with respect to x of e to the x is e to the x. That like feels like magic. It's its own derivative. Okay, so we're going to prove this one because the proof is awesome. It does some really cool stuff. All right, so let's see. If I actually go back to the limit definition, the derivative of e to the x should equal the limit as h approaches 0 of e to the x plus h minus e to the x over h. Okay, so if I have a power and I'm adding, that can be turned into a product. Limit as h approaches 0 of e to the x times e to the h minus e to the x over h. Okay, so this is going to be equal to, well, h is only, all right, the only thing that's going to 0 is h, so I can pull that e to the x out, and this is going to give me the limit as h approaches 0 of e to the h minus 1 over h. Okay, so we're going to play a little game here with a change of variable. Okay, so let's let some variable, I don't know, let's call it w, equal e to the h minus 1. Now, this means that e to the h is equal to w plus 1. Okay, so this means that h is equal to the natural log of w plus 1. All right, and as h is going to 0, right, as h is going to 0, this is going to 1. 1 minus 1 is going to 0, so w is also going to 0. So my limit here is now e to the x times the limit as w approaches 0, right, of w over the natural log of w plus 1. Okay, so let's make a line here so that we're not bunching this all up. That's an interesting place to be. All right, so I'm going to do something interesting here. I'm going to divide top and bottom by w. So if I take that limit, I have e to the x, right, is the limit, of w approaches 0 of, now, let's see, w divided by w is 1. And now I have 1 over w times the natural log of w plus 1. Okay. Oh, but something interesting happens here. Because then I have the limit as w approaches 0 of 1 over, and if I have a coefficient in front of a logarithm, I can bring that up as a power. So that's the natural log of w plus 1 to the 1 over w. Okay. The natural log is a continuous function, so I can bring that limit into the inside. This is going to be e to the x times 1 over the natural log of the limit as w approaches 0 of w plus 1 over 1w. Okay, so that's a little weird, right? Lots of work here. All right, so I'm going to carry that thing to a new page. So let's take that. That's e to the x, 1 over the natural log of the limit as w approaches 0 of w plus 1 to the 1 over w. So let's copy that on my new page here. We have, at this point, the derivative with respect to x of e to the x is equal to e to the x times 1 over the natural log of the limit as w approaches 0, right, of w plus 1 to the w. Okay. That's a lot of work to carry that over, but we got it. So we're going to do another change of variable. We're going to let z be 1 over w. Okay, so what does that do? That gives me e to the x 1 over the natural log. Okay, so let's think about this. If w is going to 0, z has to be, this is getting bigger. It's going to go to infinity. So this is the limit as z approaches infinity. All right, let's see, w plus 1. Oh, let's think about that. All right, w plus 1. So if z is equal to 1 over w, if z is equal to 1 over w, then w is equal to 1 over z. W plus 1 is equal to 1 plus 1 over z. Okay, so this is w plus 1 is 1 over 1 plus z, 1 plus 1 over z, and 1 over w is z. Okay, so that should all line up. Aha! Here's the cool moment. This limit, we know. This limit should be familiar. The limit as something goes to infinity of 1 plus 1 over that something to that something just happens to be e. So that's the natural log of e And the natural log of e is 1, and 1 over 1 is 1. So now we have this just equaling e to the x, which means we have proven that the derivative with respect to x of e to the x is in fact e to the x. Freak of nature, there it is. Okay, never have to prove it again, but it's there. Make a little box there. Feel happy about it. Okay, so, all right, so that gives me number 1, the derivative with respect to x of e to the x is e to the x. All right, great. Number 2, what do I get if I take the derivative with respect to the x of the natural log of x? Okay, this seems like it should be as equally complicated to prove something. The answer here is that this is 1 over x. Seems like how'd that happen? Okay, so let's get the y. All right, so let y equal the natural log of x, right? Then this implies that x is e to the y. That's what that means. These two things are interchangeable sentences. So use your implicit differentiation. Dx over dx is e to the y, chain rule dy dx. Aha, because we just proved that e to the y is e to the y, but we have a chain rule here because we're differentiating with respect to x. Okay, so this means 1 is e to the y dy dx. Okay, great. So let's keep going here. This means that dy dx is 1 over e to the y. But now look back. E to the y is x. So dy dx is 1 over x. Haha, that works. All right, so because we took all the time to prove the E1, that makes this one work, that the derivative with respect to x of the natural log of x is 1 over x. All right, so that gets me 2. All right, number 1, the derivative with respect to x of e to the x is e to the x. Number 2, the derivative with respect to x of the natural log of x is 1 over x. All right, so what about the general cases? That's what we're down to. All right, so number 3, the derivative with respect to x of, let's do a to the x, right, some number that's not e, is actually going to be a to the x times the natural log of a. Huh? Why does that work? Okay, so note. A to the x is equal to e to the natural log of a to the x. Okay, e and natural log undo each other, right? Well, but if that's there, I can bring that out in front, so that's the same as e to the x times the natural log of a. And if I use my chain rule here, the derivative with respect to x of a to the x should be the derivative with respect to x of e to the x times the natural log of a, which should be e to the x times the natural log of a, right? Times the natural log of a using the chain rule. But if I look at this, e to the x times the natural log of a is just e to the x Let's back that up a minute. E to the x to the natural log of a is just e to the natural log of a to the x times the natural log of a, and that just, the e and the natural log undo each other, so that just gives me a to the x times the natural log of a. Aha! So that proves this one. Okay, so let's recap our list one more time. We now have 3. Number 1, the derivative with respect to x of e to the x is e to the x. Number 2, the derivative with respect to x of the natural log of x is 1 over x. Number 3, the general exponential, so some constant to x, is just a to the x times the natural log of a. And finally, number 4, the derivative with respect to x of the log base a of x. So let's figure out what that one's going to be. That is very similar. It's just 1 over x times the natural log of a. All right, so let's look at why that one works. If I take the derivative with respect to x of the log base a of x, this is the same as the derivative with respect to x of the natural log of x over the natural log of a by the change of base formula. This comes out as, well, let's see. Natural log of a here is a constant, so that can come out in front, which is just the derivative with respect to x of the natural log of x, which we know is 1 over x. So this combines to give me 1 over x times the natural log of a, which is what we just said it was here. All right, so there are your 4 logarithmic ones that you need to know, logs and exponentials. E to the x is e to the x. Natural log of x is 1 over x. A to the x is a to the x when a with the natural log of a. And log base a of x is going to be 1 over x natural log of a. So like these two are very similar. You just multiply by the natural log of a. And these two are very similar. You just divide by the natural log of a. All right, so there you go. It's a bit of a long group, but we got inverse trig functions, exponentials, natural logs, general exponential, and log base a.